and welcome to Module 9 of Lecture 1. In this module, we're going to discuss non-experimental designs, primarily observational studies. These are situations in which we can't conduct experiments, so instead we have to collect data as they are, and then study them, and try to use the same logic of causal inference we did before, without the benefit of randomization. So a lot of the same challenges exist as we had before. The same four hurdles we discussed last time still apply. We have to avoid spuriousness, we have to have causal theories, and so on. Those are all still true. Now there are different and additional challenges we have to face, though, in observational studies. Okay, so let's back up a second. What exactly is an observational study? As I just said, it's taking the world as it is, not randomizing over treatment and control groups, rather just looking at how things are and trying to study naturally occurring differences between units. As we discussed several times before now, there are different kinds of observational studies. Some are cross-sectional, in which many units are sampled in a single time period. Some are time series, in which you have a single unit sampled over multiple time periods, like the kinetic and speeding example from before. I should say we've been using cross-section versus time series. There are certainly cases when you have both at the same time, variation both across time and space, like in panel studies in which you have, say surveys on multiple people across multiple time periods. Those are usually great data sets, but they're often more difficult to get because it's difficult to get the same people to sign into the same survey over and over and over again. Anyway, at least it's more costly. So, however, that said, we're going to focus on these two extremes as if they're the only things at the moment. Okay, so reiterating dataset structure. So we have these cross-sectional studies, which are variation across space, and time series studies, variation across time. Here's an example of cross-sectional data, a different one from before. It's debt and unemployment cross-nationally. Debt is a function of GDP and unemployment rates. So it's a cross-section because it's taken at a particular snapshot in time, but applies to multiple units at the time period. In contrast, here's two different time series from 2002 across 2002, both presidential approval ratings and the inflation rate. Okay, so and those vary across time, but for a single unit. So let's go into an example now to make it a little clear what we're going to be doing here with observational studies, because most of this course is going to focus really on how to test hypotheses in the context of observational data. So we can ask the question, what's the effect of incumbency on Democratic vote share in the U.S. House elections? Now, I should say the Democratic inclusion here is not really relevant. You have to pick some party in general. You could also ask the question of what's the effect of incumbency on all vote shares. It depends on how wide a scope you want from your model, but it might be different that incumbency has different effects on different parties. So we have to pick one for what to look at the moment. Okay, and again, see, we also look at U.S. House instead of the Senate or the presidency. Again, we're sort of narrowing the scope of the generalizability of our theory at the moment just to get a sense of what's happening. Okay, so the ideal way to answer that research question would be experimental. So you have districts that have certain properties, and you look at them when there's a Democratic candidate who is not the incumbent, and that's like a control group. Then do the same exact thing and have that Democratic candidate now be an incumbent. If that were possible, then you'd have two identical districts in all ways, in which one had an incumbent and one didn't. And if you did that across multiple districts, you could have a population of different districts that were the same in all cases, except for the treatment of incumbency. That would be great. Of course, that's impossible. We can't go back in time and recreate the entire district, nor can we clone our districts and have two of everything. Right? This is not really possible. So instead, what we're going to do is hope that the group of states that have incumbents, so the group of House elections that have incumbents, and the group that doesn't, is close enough to the same that it's kind of like randomization. That's not going to work, so just a little preview, we're going to try to control for things that might be different. To do this, though, we have to start off by collecting data on the elections. So we collect time series data on these elections because we care about them across time. So first, we're going to look at the percentage of Democratic candidates who were incumbents. We're going to take data on that. And we'll also collect data on the percentage of Democratic seats after the election. We're going to try to see if there's a correlation between incumbency and and winning and seat share. And then we'll compare across elections to see if it's consistent. Okay, so this, and I should say this is a time series, not a panel, because we're basically averaging across all the states, all the House elections in the country, putting in a big pile, figuring the percentage that have incumbents and the percentage that don't, obviously, and then seeing how often the Democrat is elected in the states with incumbents and the states without incumbent Democrats and with incumbent Democrats. So we're comparing groups of states at different time periods. So the entire population is the unit here, and percentages of the population that have incumbents or do not have incumbents. Okay, so here are the data from 2004, 6, and 8, and we see is when you don't have a Democratic incumbent, the chance of election is low. It's below 40%. When you do, it's more than 70%. That seems very large, right? We all know that if you spend any time reading political science, you know about the incumbency advantage. It seems sizable. That's true in a large variety of contexts. Here, it seems to support that. A 30% chance of victory due to incumbency seems very, very large. But the problem is we can't necessarily make that statement, because incumbency itself is not randomly assigned. Districts with Democratic incumbents, right, are quite likely very different than districts without Democratic incumbents in a lot of cases. Meaning the reason Democrats win more often in districts with Democratic incumbents might not be due to incumbency, but rather due to characteristics of the district that lead to both incumbency and Democrats winning. Right? This is an example of spurious causation. Underlying factors, right, might lead to both incumbency for Democrats and Democrats winning elections, which kind of makes sense, right? The more Democrats win elections, the more often they're incumbents. So, what can we do about that? So we can do, primarily what we do is we control statistically for other factors. So what we do is we add a bunch of control variables that incorporate other things that might explain why the different districts are different, why Democratic winning districts are different from Republican winning districts, for instance, and other factors that might explain that difference that are not incumbency, and we include them in our models so as to control for them. When we do that, we find the incumbency advantage goes down to about 9% from 30. So it's still very substantial, still very powerful, but controlling for a whole bunch of stuff, we see it as still fairly substantial, but it's still only 9% instead of 30. So we get a better measure, effectively, of the incumbency advantage by controlling for the other stuff that might have led to the same outcomes as incumbency seems to have. There are other ways to do this too. Another way would be rematches. So we discussed very briefly under experimental designs the idea of matching. It's not experimental, but we discussed there the idea of matching. So you find situations that are very similar except for the treatment. Right? In this case, a rematch is kind of like that, right? So let's say we have an open seat in time period 1, and there's a Democrat running against a Republican, for instance, in the U.S. context, and let's say the Democrat wins. In the next period, let's say the Republican from the first period runs again, so it's a rematch. The only difference now is the Democrats in office is now an incumbent. So we can compare elections in which, in elections that are like the first period's election with elections that are like the second period's election. And we get a natural control for the district properties because of the same exact district in both periods. Now, it's not perfect. Things could have changed between period 1 and period 2 that we didn't take into account. Lots of other confounding factors can matter, but it's a way potentially of isolating the effect of incumbency when you sort of control for many other different district characteristics. There are also ways to do that kind of thing statistically with different kinds, like fixed effects and things, get this partially. We won't get to that in this course, but if you go on in learning research methods, you will learn more about that kind of thing. There are ways to try to control for all the various differences between units that might confound your inference. Okay. In general, though, we're going to focus on control variables as a way to do that in this course. In experiments, we control for these through random assignment and selection by holding specific values of x constant, right? So we have a treatment and a control group. So in the treatment group, x is one value, and in the control, it's a different value. We can't do this in non-experimental settings. So instead, we statistically control for x's we want to hold constant. So what we do is we measure a whole bunch of other independent variables that we call controls that we think might also explain variation in the dependent variable, and thereby might confound our inference as to what effect our primary independent variable of interest has on our dependent variable. So we measure these things, and we use statistics, as we'll learn about in this course, that permit us to estimate the impact of a given x upon y as if all the control x's were held constant. That's key. So we effectively treat things, instead of actually randomizing to create constant values, similar values of particular control variables across different groups, across treatment and control groups, we use statistics to treat the effect of x on y as if all those other observed variables were held constant. So since they don't vary in that context, their variation can't explain variation in y, and so the remaining variation in y may be due to x. Now I say maybe because this only works if you actually measure the things you want to control for and include them explicitly. Unlike randomization, inference, and experimentation, we don't get the benefit of controlling for unobserved data, right? If we didn't include it, if we didn't measure it and include it explicitly in our statistical analysis, we do not control for it. So even though we might have controlled for a lot of things and said, oh, it looks like our x affects our y because we controlled for this other stuff that seems to have mattered, there might be additional variables we failed to measure and failed to control for that actually drove the outcome. And that's problematic. And that's not even to mention that the variables we did control for might have more complicated interactions with our primary independent variable, such as interactions we discussed earlier. So we can't. So this doesn't work nearly as well as an experiment, but it can work, and it's much better than nothing, right? We can make progress towards understanding the world by using data that exists in the world already, even if it's not experimental, even if it does not come out due to randomization. We can use statistical control to get a sense of how x affects y, holding the other variables constant, in effect, that we measured. And that's also, I should say, why theory is so important. A good theory will help you determine which possible variables were important in the first place and help you focus on using those for controls instead of the whole field of every possible variable. In essence, the theory you produce limits the number of variables you should consider as controls. That's important. Okay, just to conclude this section, to conclude research design here, theory drives design, and good design helps establish the validity of your causal inferences, helps you consider other factors that might be moving the dependent variable, such as spuriousness, and helps you control for other factors to allow comparison across like units. Because again, the goal is to create like units that are close to the same as possible, accepting only the difference in the treatment, in the independent variable of interest to you. Okay. That'll be it for research design. We'll be now moving on to measurement issues. Thank you very much.